There is a stove made from 16 fire bricks and a bag of perlite that will boil 5 gallons of water using a handful of sticks the width of your thumb. It costs about $35 to build. It burns 90% less fuel than an open fire. It reaches internal temperatures above 1400 degrees Fahrenheit, hot enough that the smoke itself catches fire before it ever leaves the chamber. The design has been tested by Aprovecho Research Center in Cottage Grove, Oregon, across 30 laboratories in 15 countries. Over 10 million of these stoves have been built worldwide, and yet almost every version you will find on YouTube does not work properly. The comments are always the same: too much smoke, weak draft, burns through wood like a campfire, cannot hold a boil. 90% of those failures come down to a single number, one ratio that the original engineer spent 2 decades refining. One calculation that separates a rocket stove from a smoky hole in a stack of bricks. Nobody put that in the thumbnail. That is not an accident. The answer starts about 2,000 years ago, underneath the marble floors of the Roman Empire. The Romans had a problem. They had conquered territory stretching from the deserts of North Africa to the frozen banks of the Rhine. Soldiers and citizens in northern Gaul and Britain were freezing. An open hearth, the kind you see in every medieval painting, throws roughly 5% of its heat into the room. 95% goes straight up and out the chimney. So Roman engineers invented the Hypocaust. The word comes from the Greek, hypo meaning under, kausis meaning burning. They built a furnace outside the building and channeled the hot combustion gases underneath a raised stone floor, supported by rows of short brick columns called pilae. The heat radiated upward through the stone, warming the room from below. Smoke and exhaust vented through hollow channels built into the walls. It was the first central heating system in the Western world, and it worked so well that Roman legions built bathhouses with hypocausts in the frozen forests of Britain, 2,000 miles from Rome, and kept them at comfortable temperatures through northern European winters. Here is the part that matters. The Romans figured out something that most modern builders still get wrong. They understood that the pathway for the hot gases had to maintain a consistent cross-section from the furnace through the floor void and up through the wall flues. If the channel narrowed at any point, the draft choked. Smoke backed up. Heat concentrated in one spot and never reached the far rooms. If it widened, the gases slowed and cooled before they could transfer their heat. The whole system depended on one thing: not the size of the fire, not the type of wood, not the thickness of the floor, the ratio of the channel. Consistent from start to finish. Meaning, the size of the hole matters more than the size of the fire. 2,000 years later, in 1980, a mechanical engineer named Larry Winiarski walked into a research center in Cottage Grove, Oregon, and rediscovered exactly the same principle. He called his design the rocket stove. He spent the next 4 decades testing it, refining it, and teaching it in villages from Central America to Sub-Saharan Africa. Winiarski distilled the entire design into 10 engineering principles. But there is one that overrides all the others. Aprovecho calls it the constant cross-sectional area rule. The physics do not negotiate. Now here is where the money comes in. The average American household spent $976 on heating last winter alone. That is the national average. In the Northeast, households heating with oil paid closer to $2,500. Over a 30-year mortgage, that is somewhere between $29,000 and $75,000, just to keep the inside of your house above 55 degrees. The United States HVAC industry, just the equipment and services, not the fuel, generated over $65 billion in revenue in 2025. 117,000 contractor businesses, 600,000 employees. A machine built on the assumption that you will always need their machine. A rocket stove built from fire bricks and perlite does the same thermodynamic job, converting solid fuel into usable heat at an efficiency that rivals or exceeds a modern EPA-rated wood stove. For $35, with no moving parts, no electricity, no service contract. So why has this design, tested across 15 countries, documented in peer-reviewed studies, proven by over 10 million units in the field, never appeared in a single mainstream American home builder catalog? Why does the heating equipment segment alone account for 69% of that $65 billion market? Why has every home you have ever lived in come pre-wired for a system that bills you monthly instead of a system you build once? Why does every hardware store in America sell fire bricks in the garden section, but not a single one puts them next to a $20 pamphlet that says, "Here is how to heat your house"? You already know the answer. It is not because the design does not work. It is because a stove that lasts decades, runs on sticks you pick up off the ground, and requires no service contract is a terrible business model. That is not a coincidence. Here is your shopping list. 16 standard fire bricks. Home Depot sells them for about $2.50 each. Lowe's carries them at roughly the same price. Total $40, though you can often find used fire bricks at salvage yards for $1 each or less. If you scavenge, 16 bricks runs you about $16. One 4 cubic foot bag of perlite. Home Depot garden section, about $18. This is your insulation. Without it, you have a smoky brick pile, not a rocket stove. Do not skip this. A 5-gallon metal bucket or a number 10 tin can for the outer shell if you are building a cooking model, free to $5. If you are building an 8-inch system for a mass heater, you will need a 55-gallon steel drum. Used drums run $10 to $30 at industrial surplus, optional but recommended. A small bag of fire clay or refractory mortar, about $12 at Home Depot for a 25-pound bag, helps seal the joints for long-term use. Total cost for a cooking rocket stove, $35 to $50 new. Scavenged, under $20. Now, here is the calculation that matters. The internal cross-sectional area of your feed tube, your burn tunnel, and your heat riser must be the same at every single point in the system. Write that down. If your burn tunnel is 4 inches by 4 inches, that is 16 square inches of cross-section. Your feed tube must be 16 square inches. Your heat riser must be 16 square inches. If any segment narrows, you create a bottleneck. The draft chokes, combustion gases slow down, temperature drops below the threshold for secondary combustion, which is around 1100 degrees Fahrenheit. Below that temperature, the volatile gases that should be burning inside the stove escape as smoke instead. This is the #1 reason 90% of YouTube rocket stoves fail. People build a nice wide burn chamber, then connect it to a skinny pipe for the chimney, or they narrow the throat where the horizontal burn tunnel meets the vertical heat riser, or they shove a pot down on top and block the exhaust gap. Here is the rule. Aprovecho's original research calls it the 0.75 constant cross-sectional area rule. The channel gap around your cooking pot should maintain at least 0.75 times the cross-sectional area of your combustion chamber. Drop below that and heat transfer efficiency collapses. Step 1. Measure your combustion chamber opening. A standard fire brick is 4.5 inches by 9 inches by 2.5 inches thick. Stack them to form a 4.5-inch square channel. That gives you roughly 20 square inches of cross-section. This is your baseline number. Every other measurement in the entire stove is derived from this. Step 2. Build your J-shape. Lay bricks to form a horizontal feed tube the same width as your combustion chamber. The feed tube length should be 12 to 16 inches. Inside the feed tube, place a brick shelf 1/3 of the way up from the bottom. This is critical. Fuel sits on top of the shelf. Air enters below it, preheats as it passes through the burning charcoal bed, and feeds the fire from underneath. That preheated air is what drives the temperature high enough for secondary combustion. Without the shelf, cold air floods the fire from all directions. The temperature drops, and you get smoke instead of a clean, roaring flame. You will know the shelf is positioned correctly when you light the stove and hear a low, steady roar within 2 to 3 minutes. That sound is the draft pulling hard through the system. If you hear crackling and popping but no roar, the shelf is too high or too low. Adjust by 1 brick thickness and test again. Step 3. Build your vertical heat riser. Same internal dimensions as the burn tunnel. This is non-negotiable. The height of the heat riser should be at least 4 times the diameter. For a 4.5-inch system, that means a minimum of 18 inches tall. Taller is better. 24 to 36 inches creates a powerful draft that pulls air through the system aggressively. You will feel the suction at the feed tube opening with your hand. That pull is the engine of the entire stove. Step 4. Insulate. This is the step that separates a functional rocket stove from a decorative brick pile. Pack perlite around the outside of the heat riser. You want at least 2 inches of insulation on all sides. Perlite traps air in tiny glass bubbles. It keeps the internal wall temperature above the threshold for secondary combustion. Without this insulation, the walls absorb too much heat, the internal temperature drops, and the smoke never ignites. Vermiculite works as an alternative if you cannot find perlite. A mix of wood ash and clay also works in a pinch, though it is less effective. Here is the part that ruins 90% of builds. People skip the insulation because the stove seems to light fine without it. And it does, for the first 20 minutes. Then the draft weakens, the fire gets sluggish, smoke pours out the feed tube instead of being pulled upward. They add more wood. which makes it worse. They conclude the design does not work. They go online and leave a comment saying rocket stoves are overrated. The stove was not the problem. The missing 2 inches of perlite was the problem. For outdoor cooking, set your pot on supports that maintain a gap of 6 to 10 millimeters between the pot bottom and the stove top. Too close, and you block airflow. Too far, and you lose heat transfer. The pot skirt, if you use one, should maintain a 6 millimeter gap around the sides of the pot. This channels the hot gases tightly around the cooking surface and can push thermal efficiency above 50%. For a rocket mass heater, which heats an entire room, the exhaust from the heat riser enters a horizontal run of 6-inch stovepipe embedded in a thermal mass bench made of cob or masonry. The hot gases snake through 20 to 30 feet of pipe, surrendering their heat to the mass before venting outside as barely warm exhaust. 1 or 2 hours of a hot fast fire heats the bench, and the bench radiates warmth for 12 to 18 hours. For extreme cold, a 6-inch system handles up to 600 square feet. An 8-inch system, built inside a 55-gallon drum, handles 800 to 1,200 square feet. The drum captures the radiant heat from the top of the heat riser and pushes it outward into the room. Builders in Montana and northern Oregon have documented heating full-sized cabins through winter on 2 to 3 cords of wood per season. For comparison, a conventional wood stove in the same climate burns 6 to 8 cords. And here is a use most people never consider. The same J-tube design, scaled down to a 3-inch system, makes a backpacking stove that boils a quart of water in under 4 minutes on a few handfuls of twigs. No fuel canister, no propane, no weight. Same physics, same ratio. One more thing, fuel size matters more than fuel quantity. Thumb diameter sticks, not logs, not split firewood. Thin sticks create tall, hot flames that reach 1,000 degrees Celsius at the combustion point. That temperature is what drives secondary combustion and clean exhaust. Fat logs smolder, thin sticks roar. The design is named after the sound it makes when it is working correctly. Now here's the honest part, because this channel always gives you the full picture. A rocket stove is not a replacement for a code-compliant heating system in most jurisdictions. Building codes in the United States generally require UL-listed equipment for indoor heating. A rocket mass heater is not UL-listed. Some counties, particularly in Oregon, Montana, and parts of the rural West, allow owner-built heating systems with an engineer's stamp or a variance. Most do not. Check your local codes before you install anything involving combustion inside a living space. Second, carbon monoxide. Any combustion device that is improperly sealed or operated in a space without adequate ventilation can produce lethal carbon monoxide. This is not unique to rocket stoves. It is the same precaution you take with any wood stove, fireplace, or gas heater. Install a carbon monoxide detector. Maintain your chimney. Do not seal a room and burn fuel in it. These are boundary conditions, not flaws. A rocket stove built to the correct cross-sectional ratio, insulated properly, and vented through a functional chimney produces less smoke and fewer particulates than most EPA-rated wood stoves. Aprovecho's testing showed that properly designed rocket stoves can reduce particulate emissions by roughly 90% compared to a traditional 3-stone fire. Here's the part that stays with me. In 1980, Larry Winiarski, a mechanical engineer with a doctorate from Oregon State, walked away from the EPA and into a small research center in the foothills of the Cascade Range. He had made what he described as a vow to dedicate the rest of his expertise to where it would do real good in the world. He spent the next 40 years in villages across Central America, Haiti, and Sub-Saharan Africa. He slept on cement floors. He carried sick children to hospitals on foot. He taught indigenous women, who were the actual experts on cooking and fire, 10 engineering principles that could be drawn in the dirt with a stick. Those 10 principles do not require electricity. They do not require an engineering degree. They do not require a monthly payment. They require that you understand one ratio, that the cross-sectional area of the air path through the stove must remain constant. That is the entire trick. The Romans knew it 2,000 years ago. Winiarski proved it in a laboratory, and over 10 million stoves later, the knowledge is still sitting in a research paper in Cottage Grove, Oregon, while a $65 billion industry generates revenue from the assumption that heating is complicated. It is not complicated. It never was. A 16-brick stove with a bag of perlite and a handful of sticks just proved that. You now know what $65 billion depends on you not knowing. If you know someone who heats with propane, oil, or electric baseboard and pays for it every single month, send them this video. They deserve to see what $35 and 16 bricks can do. Knowledge like this does not disappear on its own. It gets buried. This channel digs it back up. Thanks for watching. I'll see you in the next one.